Hello there and welcome to Lower 6 Further Maths Pure Core 1 past paper, June 2012. We are looking at my favourite proof by induction question 9 here. We're looking to prove that for all positive integers, this expression here is divisible by 5. So what we need here is lots of space to start with, and we need to start at the same place we need to start at for all proof by induction questions to prove true for n equals 1. So that means that f of 1, we need to substitute 1 into this formula, so it would be 2 to the power of 2 minus 1, add 3 to the power of 2 minus 1, which will give us 2 plus 3 is 5. Great. And that definitely is divisible by 5. Part 2 is to assume true for n equals k. So that means that f of k, which is 2 to the power of 2k minus 1, add 3 to the power of 2k minus 1, is divisible by 5. So that's what we're going to assume, and the more difficult part of this question now is to prove that this is also true for n equals k plus 1. So what's quite helpful to me to get these proof by induction started is to write down what we want to show. What we want to show is that when we find f of k plus 1, or in other words 2 to the power of 2 k plus 1 minus 1, add 3 to the power of 2 k plus 1 minus 1, that this is divisible by 5. So that's what we want to show. Let's start off with effectively the left-hand side of this expression here. So 2 to the power of, let's simplify this, 2k plus 1, add 3 to the power of 2k plus 1. Now what I want to do now is somehow link it back in with my assumption up here. On the powers I've only got 2k minus 1, on the powers here I've got 2k plus 1. So what I'm going to do is I'm going to split up this indice into 2 to the power of 2 times 2 to the power of 2k minus 1. You can see here if I was to put these back together, I'd end up with 2 to the power of 2k plus 1. And I'm going to do exactly the same thing with 3 squared times 3 to the power of 2k minus 1, pulling 2 of these 3's out of this expression on the top here. Let's write down what these indice values are. So 4 times 2 to the k minus 1, add 9 lots of 3 to the 2k minus 1. Don't mix these back up together and get 8 or 27. It's just not how you do indices. Right, so now what I want to do is group all of this expression here together. We want to group our assumptions together. So 4, and then I'm going to open some brackets and squeeze in as much as I can. 2 to the power of 2k minus 1, add 3 to the power of 2k minus 1. Great. I've got my assumption into my expression now. However, this isn't quite the same as what I had in my value above. What I've got here is only 4 lots of 3 to the power of 2k minus 1, but I need 9. So I need an extra 5 more of those 3 to the power of 2k minus 1s, which is great. What I now have is the summation of 2 components that are both divisible by 5. And I'll need to write down explanations for this, so I'm going to highlight the first part of it with a star. This star part is divisible by 5 by assumption. And the second part of this, the double star part, is divisible by 5 by an obvious factor. Maybe I didn't need to write in obvious there, but it's obvious, so I'm going to write it by an obvious factor. So therefore, by the summation of two multiples of 5, f a plus 1 is divisible by 5, which is what we had on our right hand side of our want to show. Great, so all that leaves for me now to do is to write down my conclusion. My conclusion I'm not going to write down, you can have a look for that in the answers, but it's going to read something along the lines of, given that we have proven for n equals 1, we've assumed true for n equals k, and we've also proven true for n equals k plus 1. Therefore, by mathematical induction, for all values n that are positive integers, it's really important that you recall the fact that n is a positive integer. For all n is a positive integer, f of n is divisible by 5. There we are. 5